Mathematical induction. Okay. Um, the principle of mathematical induction, that is, let P be a proposition defined, okay, defined on the positive integers, let's say n, okay. Then P of n is either true or false for each n belongs to n. Okay. Suppose P has the following properties, that is, P of 1 is true, and P of k plus 1 is true whenever P of k is true. Okay. So then P is true for every positive integer n belongs to n. Okay. And that is the principle here. Okay. Yeah. Now let us solve the problems based on this. So let us prove by mathematical induction that the sum of the first two n odd numbers is n squared, that is 1 plus 3 plus 5 plus and so on, 2n minus 1 is n squared. Okay, so let P be the proportion. Okay, let P be the proportion that the sum of the first n odd numbers is n squared, that is P of n should be 1 plus 3 plus 5 plus, okay, that is 2n minus 1 is n squared. Okay, so uh, the kth order would be 2k minus 1. Okay, and the next odd number would be 2k plus 1. Right, now we observe that P of n is true for n is equal to 1. Okay, that is P of 1 is 1 square. For n is equal to 3, yeah, so that would be 1 plus 3 is equal to this is for the n square, which is 4. Okay, yeah. Okay, now for let us assume for P of k, which is P of k, so is true when we add 2k plus 1, right, on both sides. Okay, so we obtain 1 plus 3 plus 5, okay, plus 2k minus 1 plus 2k plus 1, right? So minus k square plus 2k plus 1, which is equal to k plus 1 whole square. Yeah. So which is pk plus 1. Okay, it's pk plus 1. So in other words, pk1 k plus 1 is true whenever p of k is true. So by the principle of mathematical induction, p is true for all n. Okay, hence proved. Now let us prove by mathematical induction that for all positive integers n greater than or equal to 1, 1 plus 2 plus 3 plus 4 plus n is equal to 1 by 2 times of n into n plus 1. Okay, so here we have to prove that um, Sn is equal is 1 plus 2 plus 3 plus n is equal to 1 by 2 n plus 1, n into n plus 1. Okay, for all integers n greater than or equal to 1. Okay, so the first step is for n is equal to 1, right? So the statement is true. Okay, so that is 1 is equal to 1 by 2, 1 into 1 plus 1. Yeah, so which is clearly true, and hence it is verified for n is equal to 1. Okay, and for we assume that s of n is true for n is equal to k. So k is an integer which is greater than or equal to 1. Okay, so we assume that it is true. So s of k, that is 1 plus 2 plus 3 plus k is equal to 1 by 2 k into k plus 1, right? Yeah. Okay, so we using this we can find, yeah, by adding k plus 1, yeah, to both sides. So let us add it. So 1 plus 2 plus 3 plus k plus 1 is equal to half of k plus 1 plus k plus 1, right? So which is equal to k plus 1 1 by 2 k plus 1, right, which is equal to half of k plus 1 multiplied k plus 2, right? So this is precisely the statement of s of k plus 1. Thus on the basis of assumption s of n is true for n which is k which is greater than or equal to 1, and we have established for n is equal to k plus 1. Okay, so the proof is this, right? Hence we have proved it. Okay, so let us prove that s of n for n factorial greater than or equal to 2 to the power of n minus 1, okay, is true for all integers n greater than or equal to 1. Okay, so what is the first step? For n is equal to 1, for n is equal to 1. Okay, so Sn, that is 1 factorial greater than or equal to 2 to the power of 1 minus 1. So which is obviously true. So S of n is verified for n is equal to 1, right? Now the next step is Sn is true for n is equal to k. So this is for k greater than or equal to 1. So we assume that k factorial, right, is greater than or equal to 2 to the power of k minus 1, or 2 to the power of k minus 1 is lesser or equal to k factorial. Yeah. Now this yields to 2 to the power of k is equal to 2 multiplied 2 to the power of k minus 1 less than or equal to 2 multiplied k factorial, because we know this, right? Now this is less than k plus 1, yeah, into k factorial, because 2 is less than k plus 1, that is for k greater than or equal to 1. Okay, and now this is equal to k plus 1 factorial. Okay, so k plus 1 factorial is greater than or equal to 2k, 2 to the k. So this is precisely the statement S of n for n is equal to k plus 1, right? So on the assumption that S of n is true for n greater than or equal to k greater than or equal to 1. Yeah. So we have proved that S of n is true for n is equal to k plus 1. Okay, so hence by mathematical induction, S of n is true for all integers n greater than or equal to 1. Okay, so let Sn here, Sn be the given statement. Okay, so we note that for S of 1, for n is equal to 1, so 5 divides 1 to the power 5 minus 1, okay, which is equal to 0, right? So this is true. Okay, so we assume that S of n is true for n is equal to k, where k is greater than or equal to 1, and that is we assume that for k greater than or equal to 1, so 5 divides, so 5 divides k power 5 minus k. This means that k power 5 minus k is multiple of 5, that is k power 5 minus k, which is 5 times m, okay, for some positive integer m. Okay, so consequently we can find that k plus 1 to the power of 5 minus k plus 1, right? Yeah, so this would lead to k power 5. Okay, now further, k power 5 minus k can be written as 5 multiplied m, okay, plus 5 k power 4 plus 2k cube plus 2k square plus k. Right? Now this will be equal to 5 times of m plus k power 4, 2k cube, 2k square plus k. So this shows that k plus 1 to the power 5 minus k plus 1 is a multiple of 5. So 5 divides, right, k plus 1 to the power 5 minus k plus 1. Yeah, so this is precisely the statement. S of k plus 1. Okay, so S of n is true for every positive integer n.